Okay, this video is going to cover the supplemental material that was not typed into your guided notes. So the first theorem is the similar right triangle theorem. And it says if the altitude is drawn to the hypotenuse of a right triangle. Now altitude is a fancy word for the height, that perpendicular piece. This guy right here is drawn from the right angle to the hypotenuse in a right triangle. This only works for right triangles. Then the two triangles formed are similar to the original and to each other. Now there's a lot of words there, but basically by drawing CB where it is, you get three similar triangles. And I'm going to color code them because you know how I love my color. So I've got the big guy, and I'm going to draw them out separately. And then I have the first little guy, which is right here. And then I have another little triangle right here. These three triangles are all similar. And so that gives us a huge opportunity to write proportions and solve for missing pieces. Now let's think about our similarity statements that are going on here. Labeling these can be a little tricky, and so I always like to start with the right angle. And so if I start with the right angle of the big blue one, that is at C. And then I'm going to continue down the shorter leg to A, and then continue across the hypotenuse to D. Now I'm going to repeat that pattern with my yellow. My right angle of my yellow one is B. My shorter side here goes to A. Down my hypotenuse this way to C. For my blue triangle, my right angle is again B. My short side is to C, and then down the hypotenuse to D. Each one of these is similar. And if I were going to write that similarity statement, I would say triangle CAD is similar to triangle BAC, which is similar to triangle BCD. Once you have them drawn separately, it's easy to see, but when they're all overlapped and turned, it often can be kind of difficult to see. So, example, draw each similar triangle separately and write the similarity statement for all three triangles. So let's color code them. Here's our big guy. And then we have a little guy here in blue. And I'm going to exaggerate the short side and the long side in them for our picture. And then we have the guy in red. All right, so starting with my big green one, my right angle is F, up the short side to H, down the hypotenuse to G. When I look at the blue triangle, I is my right angle, down my short side to H, and down my hypotenuse this way to F. For my red triangle, I is still my right angle. This time my short side, my short leg, goes up to F, and I run down my hypotenuse to G. So my similarity statement will be triangle FHG is similar to triangle IHF, which is similar to triangle IFG. We could solve and set up any necessary proportions from that. Now the next piece that's on your supplemental note is this idea about geometric mean. This is actually a calculation. We're used to thinking about mean in terms of adding and dividing by the number you added. This is a different kind of mean. So what it does is it sets up A over X is equal to X over B. There's your formula. X is always positive. Questions are going to look as straightforward as this. Find the geometric mean between 2 and 31. 2 and 31, the numbers are always your A and your B, and so you're going to have 2 over X, which is equal to X over 32. Just remember they're opposite each other. When you cross multiply, you end up with x squared is equal to 2 times 32. X squared is 64, and x is 8, because I only have to think about the positive. Now, what does this have to do with geometry? Well, there's a geometric mean theorem, which says if the altitude is drawn to the hypotenuse of a right triangle, our same altitude that makes similar triangles, then the measure of the altitude, in this case x, equals the geometric mean between the measures of the parts of the hypotenuse. So that segment dropped from the right angle to the hypotenuse cuts it in two pieces. Those two pieces are in a relation of the geometric mean to the hypotenuse. So we can have a picture like this. Now you could pull this all apart and use similar triangles, but this is kind of a shortcut. So in finding x, we are going to use the geometric mean theorem, which says that x over 6.5 is the same as 26 over x. When you cross multiply, you get x squared is equal to 6.5 times 26. X squared is 169. X is 13. Now, this becomes kind of a fun problem, because if x is 13, now I have one right triangle here that I can use the Pythagorean theorem on. Y squared is equal to 13 squared plus 26 squared. And when you do that math and square root, you'll find that y is 29.1. And then if I turn around and I use 13 with the other triangle in a completely separate problem, I end up with z squared is equal to 13 squared plus 6.5 squared. And when you square those, add them, square root it, z ends up being 14.5. So that Pythagorean theorem, useful little theorem, always comes in handy with right triangles. And then the geometric mean helps you solve very quickly and without a ton of thought for that altitude piece.